Okay, so section 11 is a very important section because we use it not only in complex, but we also use it in reals. So I want to spend a little time talking about some of this material. The first thing we have to understand is what's called an epsilon neighborhood of a point z naught is. And basically, we're given some point z naught, and we're looking at the set of all points within epsilon of z naught. Okay, so this is going to be some length epsilon, and these are all the points that are going to be less than or equal to a distance of epsilon from z naught. And really, if we want to be careful, we actually have to draw a dotted line. Okay, we're not considering the circle itself. Okay, so this is all the points that are in the interior of this circle. And this is said to be the epsilon neighborhood of z naught. Okay? We use NBD for neighborhood. Now, why do we care about that? Well, because we're going to want to look at some set in the complex plane. Let's just call it S, okay? So I want to look at some point S in the complex plane. And I'm going to draw it in a very general way, okay? I'm going to draw it like this. And I'm going to include the inside. Notice that not all the points on the boundary are included. The dotted lines mean those points are not included, okay? And what I'm going to see is that for any set of points, there's always three sets of points associated with it, okay? First, there's what's called the interior points, okay? So this point is an interior point of the set S. And the reason why is there is some neighborhood around that point that's entirely contained in the set S. So notice that this neighborhood right here, I'm going to draw it like this. Okay. This neighborhood of this point is entirely contained in S, right? So this point, I'm just going to call it Z1. Z1, that's this point right here. That's an interior point. So whenever I can draw a little ball, and that ball is entirely within the set, that's an interior point. So Z1 is an interior point of S. Okay. Now, there are some points that lie outside the set. And how do we define that? Well, let me take this point here. The way I'm going to define it lying outside the set is I'm going to say that there is some epsilon neighborhood around that point that lies totally outside of S. Okay, so this is called an exterior point. Okay, so there exists a neighborhood. There exists a neighborhood containing no points of S. Okay, so notice this neighborhood here does not contain any points of S. Let me draw in a different color so it's not confusing. This neighborhood right here contains no points of S. So Z2 is an exterior point. Of S. Now you notice there are some points that are neither. The points on the boundary are neither one. Notice if I choose this point here, no matter how small I draw the epsilon neighborhood, there are always points in S and not in S. Okay, so I can never draw a neighborhood of this point that lies either entirely in S or entirely outside of S. So these are called the boundary points. Okay. Z3. So these points here are all boundary points. Notice that even if the point's not contained in the set, okay, it can still be a boundary point. Like this point here is not contained in the set, but it's a boundary point because no matter how small I draw that neighborhood, it's never totally in one set or totally in the other. This is a boundary point of S. Okay? And now we're going to define some types of sets, okay? We're going to say that a set is open if it doesn't contain any of its boundary points. So let's take a look at an open and a closed set. So here's an example of an open set. Suppose I take a circle of radius 1 about the origin, but I don't include the circle, just the inside. Okay? So remember that dotted line means that those points are not included, right? And I claim that this is going to be an open set. What do I have to do to prove that? Well, I have to prove it doesn't contain any of its boundary points. Well, it doesn't, because these are the boundary points. They're not in the set. Okay? Now, a set is closed if it contains all of its boundary points. So, in other words, if I had the circle and its interior, now this would be closed. Okay? Because remember what well, this is just a definition of closed. It's closed if it contains all of its boundary points, right? So this is going to be a closed set. Okay. All right. Notice that even if I didn't contain the interior, it still would be closed. Okay, so this is also closed. Even if I don't contain the interior. Okay. And if I contain the interior and the outside, it's also closed. These are all examples of closed sets. Why? Because they all contain their boundary. So this is also a closed set. Because what is the boundary of the set? Well, the boundary of the set is this inner circle. It's contained in the set. Okay? All right, now we get to the homework problems. So this is a definition of accumulation point. And what we're going to say is we're going to say that we have some set S. And now we're going to look at what's called the deleted neighborhood, okay, of Z0. So what that means is that the deleted neighborhood of Z0 is a little circle that doesn't contain Z0. Okay? So it's a circle that doesn't contain its origin. Okay. So this would be called the deleted neighborhood of Z0. And again, it would be all the points like this. Okay. This would be a deleted neighborhood. So it's an epsilon neighborhood that does not contain the center. So this is a deleted neighborhood. Whoops. Okay. Z0. Okay. Now notice what it means to be an accumulation point. It means that if you're an accumulation point of a set S, every deleted neighborhood has to contain at least one point of S. Okay, let me give you an example of an accumulation point. So here's this set. Let's make it the set 1, 1/2, 1/3, etc. Right? Now, if I plot this set of points, okay, it looks like this. 1's included, right? This is going to be 0 down here. Okay. 1/2 is included. 1/3 is included, right? And notice they keep getting closer and closer to 0, right? And what I claim that 0 is an accumulation point of this set. Okay, so let me go ahead and try to prove this. So notice that if I take any neighborhood of 0, it always contains one of these points of S. Let me draw the points of S in blue. Okay. They keep getting closer and closer. They're an infinite sequence, right? no matter how small I draw this neighborhood around 0, okay, it's going to contain 1 point from S. So we say that 0 is an accumulation point. Of S, of the set S. Even though it's not included, right? Now, what do we have to show that a point's not an accumulation point? Well, what is a negation of this, okay? Let's look at this statement logically. This says that for every epsilon greater than 0, there exists an X in S such that, well, let me say Z. Be a little. There exists a Z in S such that Z minus Z naught is less than epsilon. Okay? Now, when I negate this, whenever I negate a for every, it becomes there exists. And when I negate a there exists, it becomes a for every. So when I negate this statement, this is the negation, this little squiggly sign. What this becomes is this becomes the following statement. There exists an epsilon greater than 0 such that for every Z in S, Z minus Z naught is greater than or equal to epsilon. This says that there is some deleted neighborhood of Z naught that contains no point in S. Okay? So let's go ahead and look at the problems now, okay? So the first problem says, prove that if a set contains each of its accumulation points, then it must be a closed set, okay? So we're going to start off with some set S. Let S be a set. We'll say a subset of Z. I'm sorry, a subset of C, complex plane, such that S contains all of its accumulation points. Okay. And we didn't define closed set. So let's go back real quick and look and see how you define closed set. A closed set is a set, there's different ways of saying it. It's a set whose complement is open. That's one way. But let's look and see how the book defines closed set real quickly here. What did I do with that? Maybe it's here. Yeah, let me get out here real quick. Okay. Okay, so a set is closed if it contains all of its boundary points. Okay, that was a definition we had before. Okay, so what we want to show is we want to show that the set contains all of its boundary points. So what we have to show contains all of its boundary points. And what we're going to do is we're going to use proof by contradiction. So we're going to assume that there's a boundary point that's not in S. And assume there is a boundary point Z naught that, well, we'll say a boundary point of S Z naught such that Z naught is not an S. But we notice we're going to get a contradiction because we know that by definition of boundary point, every neighborhood of the boundary point has to contain a point in S. Okay, so if we go back to boundary point, okay, and look at the definition carefully. Okay, so a boundary point, therefore, is a point, all of whose neighborhoods contain at least one point in S and at least one point not in S. Okay, so that's what we want to focus on. Okay. Okay, every neighborhood of Z naught must contain a point of S, and therefore this implies that Z naught is an accumulation point and since we assume that S contained all of its accumulation points, this implies that Z naught is an element of S, which produces a contradiction. Therefore, S must be closed. So that's a good proof to get to know. All right? Okay. Let's see. Last problem from there, 10. So we want to prove that a finite set of points cannot have any accumulation points. And this is going to be easy to do. Again, we can use proof by contradiction, actually. It's not hard. Notice that actually any of the, well, let's go ahead. Let's just prove it. So the proof is going to be that it does have an accumulation point. So we're going to let S be defined as the set Z1, Z2, ... Zn. And let's suppose Z naught is an accumulation point of S. Okay? So we're going to suppose there exists a Z naught in the complex plane such that Z naught is an accumulation point of S. Okay, let me draw a picture. So to kind of understand the proof, here's what's going on. So here are these endpoints, okay? I don't really care so much where they're located, okay? Now, notice that Z naught can actually be one of these points. I haven't excluded that possibility, but let me just suppose that it's not. Let me put Z naught here, okay? Notice that if I choose an epsilon less than the smallest of these distances, okay, ... So this is going to be, I'm going to call this epsilon 1, this distance epsilon 2, epsilon 3, epsilon n, okay? And if I choose epsilon to be 1/2 the smallest of these distances, Notice that this point cannot contain any of the points in S. Okay? And this implies that all the points within epsilon of Z naught cannot be in S. Now we should prove that. It's obvious from the diagram, but let's go ahead and prove it, okay? So let's go ahead and show that. So what I want to do is I want to let Z be a complex number such that Z minus Z naught is less than epsilon. Okay. But notice that all of these distances are further away. Okay, so if I looked at the distance between Z and any other of these numbers, okay, well, it's actually equal to, sorry, it's equal to epsilon I, but notice that epsilon I is greater than epsilon. Because epsilon is 1/2 the minimum of these, right? So if it's half the minimum, each of these have to be greater than this. Okay, for all I. So no Zi can be in the epsilon neighborhood of Z naught. Therefore, we found an epsilon of Z naught that contains no points of S. Therefore, Z naught is not an accumulation point of S. So if I can find some little ball, some open ball, okay, that does not contain the point, okay. So I find the little open ball that doesn't contain any points in S, then that point's not an accumulation point of S. Okay, I think that's all for that problem.